So in part 3, we're going to take a look at some of the basics of electricity and magnetism and see the impact that they have on relativity. This is what we call a paradox. It seems to be a logical contradiction. At least that's how it was initially viewed. We now understand that it's not a contradiction. Imagine you've got two stationary rods, and they've got some kind of electrical charge. And whatever that charge is, it is a matching charge on both rods. Now, when people were first starting to figure out electricity and magnetism, they were doing that in the second half of the 19th century. Now, Newton's laws were developed during the 17th century, so they had stood virtually unchallenged for about 200 years. And yet we came to what seemed to be a logical contradiction. If you have these rods, it doesn't matter what reference frame you use to view them, as long as you're viewing them in some kind of reference frame, and that's somehow consistent, you will get consistent laws of physics out of them. So they're either going to repel or they're going to attract. Now, classical electricity and magnetism say they're going to repel each other. So if these are stationary in your frame of reference and you look at them, they're going to try to push each other apart. But now, let's say you're speeding by. Maybe in a jet plane, maybe in a race car. However you're moving quickly. Then when you look at these, you don't see them in your reference frame as stationary rods. You see them as moving rods. You see them with a current flowing this way. And once you have current, you have a magnetic field. And that magnetic field, as it wraps around the rod, will produce a force. If you've got two lines with parallel current, as this would be, the magnetic force is attractive. So this was what was seen as the problem, or the paradox. If you move quickly enough, you will see different phenomena. Slow-moving observers in slow-moving reference frames are going to see a repulsive force. Fast-moving observers are going to see an attractive force, because if you move quickly enough, that magnetic force is going to overcome the electrostatic repulsion. And these rods are going to come together. And if you find exactly the right speed, perfectly balanced in between, then you're actually going to see the forces cancel out completely, and these rods don't move at all. This seemed to be a massive problem. Either the rods move, or the rods don't move. You can't have it both ways. If they move, they're going to move together, or they're going to move apart. Again, you can't have it both ways. So this is what became a fundamental paradox. With Newton's laws standing for over 200 years, and with Maxwell's equations and this theory of electricity and magnetism being 10, maybe 15 years old at this point, almost the entire physics community was looking at the new stuff to find the problems there, because the old stuff had been working fine for 2 centuries. So clearly, that's going to be the one that makes sense, and that's going to be the one that's on the right track, right? As it turns out, it was the young whippersnappers that had it right, and it was Newton's laws that were going to be overturned. We will get to that in much more detail later. For today, we just know the paradox exists. We're going to have to give it a couple days before we can come back and resolve it. And next up is the other piece of information that Einstein used to really turn the world on its head, and that is the calculation of the speed of light from theory. And that is the topic of our final video for today.